My name is Meg McBean, and today I'm demonstrating electrorheological fluids. Electrorheological fluids, also called ER fluids, are a type of smart material that reacts to an applied electric field. When there is no electric field present, the ER fluid will act as a liquid. Once the electric field is applied, the particles attract each other to form congealed columns parallel to the applied electric field. At a high enough electric field, the ER fluid becomes a solid. Once the field is removed, it will return to its original state. It doesn't take much to create an ER fluid, just polarizable particles distributed within an insulating oil. For this demo, I've mixed cornstarch and silicon oil. ER fluids require low currents to maintain their solid state, but very high voltages in electric fields. They work best at a 3 to 5 kilovolts per millimeter electric field. So I've created a voltage multiplier circuit with 4 capacitors, 4 diodes, and 120 volts AC current. Winds up looking like this. So first 120 volts will enter the system, charge up the first capacitor to 120 volts, and then go back to ground. On the downward wavelength of the current, this first diode will no longer allow current to pass through since it's forward biased, so instead the current will pass through second diode and charge up the second capacitor. So now I'll wind up at 240 volts total charge. It'll continue twice more to give me 4 times the original 480 volts of charge, which is almost my 500 volts desired. Unfortunately, my circuit has fried several times now, probably due to faulty wiring, so I was unable to use the circuit in my demo experiment. So here's the setup. You can see I've got my 2 electrodes right here. They're actually picture frame hangers. I've got my positive lead, my negative lead, and what I'm going to do is I'm going to take this electrorheological fluid and I'm going to put it on these electrodes right here. And if I had a high enough electrical field and a high enough voltage being produced, then you would be able to visibly see the electrorheological fluid thickening and becoming solid, and it would stay solidly held in between the 2 electrodes. So I'm going to apply the fluid right here in the middle of the electrodes, and it just kind of runs right out. Nothing really happening there. So I'm going to switch on my voltage really quickly. And if you look over my voltmeter, got 135 volts approximately. So come back in, and if I had a higher voltage, what you'll be able to see here is the fluid staying in there for a significant amount of time and becoming a complete solid. As it is right now, it might be slowing down a little bit. The viscosity might be increasing just a tiny bit, but that's all. One of the practical uses of ER fluids is in microfluidics, which is used with minuscule labs on chips to measure proteins, antibodies, and so on in a biological setting. They use ER fluids flowing through microchannels as a sort of simplified computing system. When an electric field is applied, the ER fluid will solidify, causing a blockage in the fluid flow. Just as an example, this could represent a 1 in a binary system, and fluid flow could represent a 0. I tried to demo this by inserting ER fluid through a straw and passing it through the electrodes, but once again my electric field was too weak. The electrode plates in my demo acted similarly to 2 capacitor plates. Based on this, I was able to use Coulomb's law to calculate the electric field produced by my system as a function of voltage and the distance between the plates. I calculated the electric field over a variety of voltages. The electric field I obtained is represented by the first marker in the top left, and the field I hope to obtain with my voltage multiplier circuit is right next to it. The third marker in the right corner represents the optimal electric field for maximizing the yield strength of the ER fluid. It may seem like the first and second markers would produce very similar results, but electric field intensity causes an exponential increase in yield strength, as shown here. Here I've calculated the force experienced by 2 ER particles interacting in an electric field. You can see that the effect of an electric field on this type of ER fluid plateaus at around 5 kilovolts per millimeter. The strength of the ER fluid as it turns to solid is dependent upon the interaction strength of the ER particles, which in the case of this demo is the cornstarch. While I failed to produce a phase change with the ER fluid, the experiment did show the great voltages required for this transition. It's for this reason that ER fluid works well with microfluidics due to the lower voltages required to affect minuscule ER droplets. Thanks for listening.